second part of the video here. In this video, we're going to talk about how we can use the squeeze theorem to help us prove one of the big indeterminate limits in trigonometry. The limit as theta goes to 0 of sine of theta over theta will prove that's equal to 1. And so as usual, we're going to go back. We're going to look at some of the geometry involved, the definition of sine and cosine on the unit circle, and then the squeeze theorem is going to come in to save the day for us. So once again, we're looking at the appendix there on handout from section 2.3. We've got this diagram to play with. So going through each part of this here, this is part A. We're asked to determine the coordinates of the point Q. And so there's lots of ways to do that. But we can go back to our right triangle roots here. You notice that if I look at the triangle OQB, which I'm tracing very shoddily there, that's a right triangle. And so if I look at the tangent of theta, that's the opposite side, which would be the I'll call that h here, divided by the adjacent side, which, well, that's just going to be 1. And so that h there is the tangent of theta. So the x-coordinate is 1, and the y-coordinate is the tangent of theta. And hopefully someone told you, as you were coming up through the ranks, that that's why the tangent function is called the tangent function, because it is the length of that tangent line. So if you think about this line here, this vertical line, that vertical line is tangent to the unit circle at 1, 0, and the tangent of theta is representing that length. That was part A. So we know that this length here is tangent theta. Then using that, we can show that the area of OQB is 1/2 tangent theta. So that's tangent theta tall. The base is 1/2. So the area here of this triangle, the blue triangle there, 1/2 base times height, (1/2) 1 times tangent theta, 1/2 tangent theta. That was part B. Part C says by comparing the areas of triangle OPB, sector OPB, and triangle OQB, shows that sine theta is less than or equal to theta is less than or equal to tangent theta. So going back to what we did before, we've already shown in the previous video that the area here is 1/2 sine of theta We've already shown that the area of this sector is 1/2 theta. And we just got done showing that the area of this triangle is 1/2 tangent theta. And so if we just go through here and multiply through the inequality by 2, all the 1/2 drops out. And that's exactly what they wanted here for part C. They wanted that the sine of theta is less than or equal to theta is less than or equal to the tangent of theta. So you can see we're getting ready here for some squeeze theorem shenanigans. So this is what we call a compound inequality. And so this means that both of these inequalities are true. So if I look at sine theta less than or equal to theta, once again, if I'm assuming here we're in quadrant 1 and theta is a positive number, I can divide both sides by theta and get sine of theta over theta is less than or equal to 1. From the inequality theta is less than or equal to tangent of theta, I can rewrite tangent of theta as sine over cosine. And once again, assuming I'm in quadrant 1, I can multiply both sides by cosine theta because it's a positive number, and I can divide both sides by theta because it's a positive number. And I can get that the cosine of theta is less than or equal to sine of theta over theta. So now I've got the function I don't know about sandwiched or squeezed between two functions I know about. So once again, we're looking here in quadrant 1. So when we're looking at theta coming into 0, it's going to be coming in from the right-hand side. So we talked about that in the last video. If we're in quadrant 1, this is theta equals 0, and these are the positive thetas. So theta coming into 0 from quadrant 1 would be the same as theta coming into 0 from the right. Of cosine of theta. And in the previous video, we proved that this was 1. The limit as theta comes into 0 from the right of 1, that's the constant rule, that's also 1. So putting these together, the squeeze theorem gives us that the limit as theta comes into 0 from the right of sine theta over theta is 1. But as we all know, we want to know the limit as theta comes into 0 from both directions is 1. And so like in the last video, when we used some of the symmetry of the sine function, we're going to use the symmetry here. If theta is coming into 0 from the left, then the opposite of theta is coming into 0 from the right. So once again, why is that true? If theta is something like negative 0.1, negative 0.01, etc., then the opposite of theta would be 0.1, 0.01, etc. So if I'm looking at the limit as theta comes into 0 from the left of sine of theta over theta, I'll make a substitution. I'll let t be the opposite of theta. So theta is the opposite of t. Theta coming into 0 from the left is going to be equivalent to t coming into 0 from the right. So this would be the limit as t comes into 0 from the right, the sine of minus t over minus t. So now we're going to use the odd property of the sine function. Like we did in the previous video. And we'll move the negative out front where it cancels out. And now we're back to the limit that we just got done proving. And so we've shown that the limit as you come into t from the limit as theta comes into 0 from the left and the right both equal 1. And so as promised, we've proven that limit. Once again, using the definition of sine and cosine and radian along with the squeeze theorem. So, what about this other limit then? This was another limit that gets used quite a bit when it comes to indeterminate forms and trigonometric functions. How do I approach this? Well, even though it's not obvious, if you think back to trigonometry, you had Pythagorean conjugates. So that word conjugate comes up again. So let's multiply numerator and denominator by that. Now, why are we doing that? Because we know that if we use a Pythagorean conjugate, we're going to be able to exchange cosine squareds for sine squareds. So this is one of those nice little sleight of hand tricks you did in trigonometry. So the Pythagorean identity, cosine squared theta plus sine squared theta is 1, which in the last video we remarked came right from the definition of the unit circle. We can rewrite this to show that sine squared theta is 1 minus cosine squared theta. So that lets us take this limit, which doesn't have any signs in it at all, to give us sines. Whoops. And why do we want sines? Because we know about limits involving sine thetas over theta. Now, we know sine theta over theta goes to 1. Here I've got 2 factors of sine, so I'll go ahead and rewrite that fraction as a sine of theta over theta. So there's a factor of sine going with that theta. And then the other factor of sine I'll group with the other piece. I know this limit's going to 1. We just got done proving that. And I know with this limit, as long as I'm not dividing by 0, I can apply the substitution rule. I know that from the previous video. So if I plug theta equals 0 into this, I would get the sine of 0 over 1 plus cosine of 0. So this limit is going to go to 1 times 0 over 2, which is 0. So I appreciate you watching this video. I hope as you followed along, you realized what all went into these proofs. But ultimately, when you get to a level like calculus, you really shouldn't have to take much for granted. You should be able to construct and derive all the formulas that you're using. And as we'll see moving into the next chapter, these trigonometric limits, sine theta over theta and 1 minus cosine theta over theta, are critical in our study of the calculus of these functions.